This video is the normal distribution, part 1. Standardized test scores tend to have a symmetric bell-shaped distribution, and in past videos we've talked about a symmetric distribution or bell-shaped distribution. We've talked about it in the form of a histogram and also in the form of a curve. These distributions are also known as the normal distribution. But what does that really mean? So if we took those standardized test scores that have this symmetric bell-shaped distribution, this normal distribution, and if we counted how many people got each score and built a histogram, we get something that looks like this picture on the left. It's symmetric. The highest bars are in the center. But if those boxes got thinner and thinner as we measured scores more finely, the histogram would take on more of a smooth curve look, like this on the right. So this curve is referred to as a bell-shaped curve. It is also referred to as a symmetric distribution, and it is also referred to as a normal distribution. So in this video, we're going to talk about other distributions that are like this, that are the normal distribution. Now, bell-shaped curves are a type of probability density function. Not all probability density functions are bell-shaped. Some are skewed left or skewed right, but it is a type of probability density function. It's like a probability distribution, and it tells us how likely a given outcome is. So, for instance, the average SAT score is 508, and the distribution of scores look like this. And what this means is that the most common score is 508. So if you look above 508, if that was a bar for a histogram, that's the highest peak. And it means that the most likely result for a randomly chosen test taker would be 508. Not only that, but the distribution gives us a precise description of how scores are clustered around the center. So let's look at these. So if you'll notice, we have 1, 2, 3, 4 normal distribution curves, bell-shaped curves, drawn on the same graph, so you can see that there can be differences. And the two parameters that define a particular normal distribution are the mean and the standard deviation, which is the spread. The mean is the center, so the center is always the mean for a normal distribution. So if you'll see, the blue curve, the red curve, and the brownish yellow curve, those all have the same mean. They're all centered around the same point. But look, the green curve, it has a different mean because its center is a little to the left of the center of the ones right here. So the mean decides where the center of the curve is going to be. Now, what defines how tall or how short one of these curves is the spread or the standard deviation. So if you look at the tallest one, it has the smallest spread, followed by the red curve, followed by the brown curve. This one is more spread out, so it has a bigger standard deviation than these two. The smaller standard deviation goes to the blue one. You'll also recall the empirical rule that we discussed in earlier videos. 68% of the data, approximately 68% of the data is within one standard deviation above and below the mean. 95% of the data is within 2 standard deviations, 1, 2, 1, 2 of the mean. 99.7% of the data is within 3 standard deviations of the mean. And you can see on the bottom here we have plus 1 sigma and minus 1 sigma for the 68%, plus 2 sigma minus 2 sigma for the 95, and plus 3 and minus 3 sigma for the 99.7. But that is a review. We have already covered that in an earlier video. So example 1 says IQ is normally distributed with a mean of 100 and a standard deviation of 16. Use the empirical rule to find the data that is within 1 2, and 3 standard deviations of the mean. So we'll start off, we'll draw a normal curve. We will label the mean, which is in the middle. It's 100. Let's do a different color. If we go up 1 standard deviation, that's plus the mean, which is 16, we get 116. So I'm just going to keep going in the upwards direction and do all the plus 16s. Plus 16 more gives us 132, and plus 16 more gives us, I believe, 148. If we go down 16, we get 84. That's minus 16. If we go down 16 more, we get 68. And if we go down 16 more, we get 52. So we have just used the empirical rule to find the data that is within 1, 2, and 3 standard deviations of the mean. So these two are within 1 standard deviation of the mean. These two are within 2 standard deviations of the mean. And these two are within 3 standard deviations of the mean. And if we want to get even more in depth, we can say that this is 68% of the data. Approximately 68% of the data falls between 84 and 116, which is within 1 standard deviation of the mean. Approximately 95% of the data is within 2 standard deviations of the mean and falls between 68 and 132. And approximately 99.7% of the data is within 3 standard deviations of the mean and falls between 52 and 148. Look at example 2. Suppose you know that the prices paid for cars are normally distributed with a mean of 17,000 and a standard deviation of 500. Use the 68, 95, 99.7 rule, otherwise known as the empirical rule, to find the percentage of buyers who paid less than 16,000. So we have 17,000 in the middle. If we go up 1 standard deviation, we get 17,500 because the standard deviation is 500. If we go up 1 more standard deviation, we get 18,000. And if we go up 500 more, we get 18,500. If we go the opposite direction, if we go down 500, we get 16,500. If we go down 500 more, we get 16,000. And if we go down 500 more, we get 15,500. Now if we want to add in our percents, that's 68% of the data approximately falls between 16,500 and 17,500. Approximately 95% of the data falls between 16,000 and 18,000. And approximately 99.7% of the data falls between 15,500 and 18,500. Now, we have defined this curve and this distribution for the prices paid for cars using the empirical rule based off the mean and the standard deviation given. However, we did not answer the question. It says find the percentage of buyers who paid less than 16,000. So here's our 16,000. What percent paid less than 16,000? Now, our empirical rule properties only tell us approximate percentages between numbers. When we say less than 16,000, the upper boundary is 16,000, but the lower boundary, we have no idea how low it goes or how low it can go. So what we're going to do is we're going to use some properties that we know about the normal distribution and the empirical rule. So first, let me tell you, look up here, a probability density function is very similar to a probability distribution function. The entire curve represents 100% of the data. If you think about a probability density function, or a probability distribution function rather, the whole thing adds up to be 1 or 100%. So the same thing is here. This whole curve represents 100% of the data. That means, what does that mean? Let me just show you. Let me draw another curve over here. That means that if I split the curve down the middle, 50% is on the left and 50% is on the right. So if I split this curve at 17,000, which is the mean, that's in the middle, 50% of the data is on the right. And 50% is on the left, but let's just stick with the right for right now. Because what we want to do is we want to find, obviously, we want to find the percentage that's to the left of that 16,000. And we're going to basically go kind of a back way to get there. So if I know from the mean all the way to the right is 50% of the data. So from 17,000 and above, 50% of the prices paid for cars are above 17,000. That's what that means. Now what I want to do is I want to find the percent of data that is between 16,000 and 17,000, and that's where the empirical rule comes in. Well, what do I know about 16,000? I know that between 16,000 and 18,000, that is 95% of the data, because that's within 2 standard deviations of the mean. But I don't want this whole 95%. I only want to know the percentage between 16,000 and the mean. Well, because the mean is the center and it splits it in half, this is half of the entire 95%. Half of the 95%. So if I divide 95% by 2, I get 47.5%. So 47.5% of the data falls between 16,000 and 17,000. And 17,000 and up to the highest price of a car is 50% of the data. Altogether, that's 97.5% of the data. Well, if I know that the entire curve is 100%, how much more do we need to make 100%? And that's what goes over here. So we need 2.5%. How did I get that? I just subtracted 100 minus 97.5%. So 2.5% of the data is less than 16,000. That's the percent of buyers who paid less than $16,000 for a car. So 2.5% is the answer. Okay, so we are going to stop right here and pick up with the next slide in part 2.